Hi, I'm Luke Kane. Welcome back to Algebra 2. Today we're going to talk about solving systems of equations using a graphical technique, but the systems of equations are going to be a little bit larger this time. We're going to look at a 3x3 system of equations, and then we're going to look at equations or systems of equations with higher dimensions. You recall, this started with a 2x2 system of equations that we got from looking at an Oktoberfest beer problem. And we solved this system of equations by plotting the lines that are represented in equations 1 and 2. And of course, where those two lines intersected was the point that satisfied both equations. Well, suppose we have a 3x3 system of equations where we have 3 equations and 3 unknowns. Well, it turns out that's going to be an equation in 3 dimensions. Let's look what it means to plot a point in 3 dimensions, and then we'll see what it means to plot an equation in 3 dimensions, and then we'll see if we can come to a solution from this system of equations by plotting them in 3 dimensions. So let's ask the question, how do we plot the point 2, 3, 2 in 3-dimensional space? Well, let's start with our familiar 2-dimensional space, the traditional XY graph that we've seen before. And we have a point at the origin, which are going to move in the x direction 2 units. And then we're going to move it up in the y direction 3 units. So now we'll end up at the point 2, 3. Now, once we get up to this point, we're going to rotate the xy plane so that it appears to be coming out at you. Now, obviously, this is a problem because we're talking about trying to represent a 3-dimensional figure in 2-dimensional space. So this is something of an illusion that artists have been working on for millennia. So now we're going to rotate this XY plane so that it's coming out at you. Now we're going to add the z-axis, which is going to be perpendicular to both the x and y-axis. That will pop out at the origin. Now let's move it over to our point 2, 3. And of course, we need to count up 2 to get to our final destination, 2, 3, 2. So we'll put in a grid, and we'll move up 2. And voila, we are now at the point 2, 3, 2. Okay, so we plotted a point in 3-dimensional space. Let's see if we can plot the graph of an equation in 3-dimensional space. Specifically this equation, x plus y plus z equals 1. It's an equation with 3 unknowns, which means we're going to have a solution with 3 coordinates, and each of those coordinates is going to be indication of the location in 3-dimensional space. So let's see if we can find a solution. Well, it turns out there's an interesting property here. All of these coefficients are 1. Okay? And what that means is that, as you're going to see, we're going to create a plane. And to create a plane, all you need is 3 points. It's analogous to the situation we had in 2 variables. Suppose we had the equation x plus y equals 1. We recall that with x and y equal 1, this ends up being the equation of a line. And that's because these 2 exponents are 1. And so all we needed to do is to find 2 points. And how do we find the points? Well, we let y equal 0 and we solved for x. Alright, so we did it again. Same process. 0 is our favorite number. Only this time we let x equal 0, solve for y. Well, we're going to do something similar. We're going to get 3 intercepts. One for the x-axis, one for the y-axis, and one for the z-axis. And when we connect the dots, we're going to have a plane, as we'll see in a minute. So let's see if we can get the three intercepts. So we do the similar procedure. Only thing that's different, really, is we have an extra degree of freedom. We can set 2 variables to anything we like, and that will determine what the 3rd variable. In other words, we have 2 independent variables and 1 dependent variable. So let's set our two variables to 0 because we love doing arithmetic with 0. And let's see what we get. So let's let y equals z equals 0. And we'll solve for x. That's easy. We get x plus 0 equals 1. X equals 1. So this gives us the x-intercept. 1, 0, 0. Hey, we can do this. This is pretty straightforward. Very similar to what we did with an equation with two unknowns. So this time we're going to let x equals z equals 0. And we're going to solve for y. Solve, S-O-L-V-E, for y. So we get 0 plus y plus 0 equals 1. Or simply y equals 1. And we have the y-intercept 0, 1, 0. And we do this one more time. We're going to let x equal y equals 0 and solve for z. So we're going to get 0 plus z equals 1. Z equals 1. So now we have the point 0, 0, 1. All right, let's see if we can take our three intercepts. All right, the first intercept is the x-intercept, and that's going to be at the point 1, 0, 0. And let's see if we can plot our second intercept, the y-intercept, at the point 0, 0, 1. And last but not least, we'll plot the point of the z-intercept at the point 0, 0, 1. Remember that our equation was x plus y plus z equals 1. And we calculated three intercepts. So let's plot those intercepts. The x-intercept is the point 1, 0, 0. And it looks something like that. And let's plot the y-intercept, which is the point 0, 1, 0. And last but not least, the z-intercept, the point 0, 0, 1. Now recall that each of these 3 points is a solution for the equation x plus y plus z equals 1. And as we learned in 2 dimensions, any line connecting those 2 points is also going to be a solution. Any point on that line is going to be a solution to our equation. Any point on that line is going to be a solution to our equation. And correspondingly, any point on that line is going to be a solution. And in fact, I can draw any line to connect that connects to either of the 2 sides of our triangle, and that's going to be a solution. And if I plot all of these points, you'll see I get another plane. And this plane essentially cuts off the corner of our coordinate system. Now, our coordinate system is basically showing one of 8 parts of a coordinate system. This is the coordinate, this is the octant, if you will, that has x, y, and z all positive. And I should finally end with a note. Although we show our plane x plus y plus z equals 1 as having edges, we realize that that's not the case. That's just an artistic convention to make the perception a little easier. So let's plot the 3 equations in our system of equations. And let's start with the last equation, the equation z equals 1. It's the simplest and the easiest to understand. Here it is, z equals 1. No matter what x and y is, z equals 1. That's represented by this purplish plane. And now if we plot the second equation, we get this. And if we plot the first equation, we get this. Now if you rotate the axes, you can see that the planes actually do intersect at a point. It's not easy to see, but we'll take a quick picture and look more systematically for the point at which all 3 planes intersect. Alright, so we're back to our system of linear equations, 3 equations and 3 unknowns. And we saw how when we plot those in three-dimensional space, we get 3 planes, and in this case the 3 planes intersect to form a solution. The first plane here corresponds to our first equation, and the same is true for the second and third planes. Now, if we look at the intersection of the first plane and the second plane, we see that it forms a line. And the same is true for the intersection of this first plane and the third plane. And those 2 lines are going to intersect to form a solution. And just to make it clear, the second plane and the third plane are also going to intersect to form a line, and that line is going to intersect with the other 2 lines. So in effect, this particular point is the only point that is common to all 3 planes. Consequently, this point is the only set of numbers x, y, and z that is going to satisfy all 3 of these equations. And it turns out for this system of equations, the solution is minus 0.8, minus 0.2, and 1. Not a number that exactly jumps out at you when you look at this three-dimensional graph. So we can conclude that although it adds to our understanding of the geometry of 3x3 systems, graphing is not a practical technique for solving 3x3 systems. Of course, raises a bigger problem. Suppose you want to graph something with a larger dimension. Suppose you wanted to graph a 4x4 system of linear equations. Well, it's simply not possible to graph systems of linear equations that are bigger than 3x3. Just no way of doing that. However, the algebra of n by n systems of equations, where n is a large number, is the same as 3x3 systems. And we'll have a little taste of that in future videos. So the point is that mathematicians end up talking about equations with n variables, where n is bigger than 3, as hyperplanes. And hyperplanes intersect in an n-dimensional space. This is pretty strange. This is a little weird. So what did we learn today? Well, we learned that graphing in 3 dimensions is possible, but it's really not practical as a technique to solve systems of linear equations. And we also discovered that graphing in higher dimensions is simply impossible. However, it's interesting to note that the algebra for solving a 2x2 system of linear equations is the same as the algebra for solving an n by n system of linear equations, where n is bigger than 3. We won't get there for a while, but we'll be able to demonstrate that in a couple of videos from now. And consequently, mathematicians infer the intersection of hyperplanes in n-dimensional space, where n is some number larger than 3, even though there is no geometric representation for something in 4 dimensions. And we learned graphing in 3D is possible. We learned that when we have an equation with 3 variables, it can be graphed as a plane. And we used a simple example of x plus y plus z equals 1. And we also saw that when we graph the planes that represent a 3x3 system of linear equations, they do intersect to form lines, and those lines intersect to form a point. That point is the solution. It is the only point, the only x, y, and z that is going to solve all 3 equations. It is a unique solution, and there are no others. So next time we're going to look at solving systems of equation by substitution, and we're going to go back to our old friend, the Oktoberfest problem. Thanks for watching. Bye for now.